Okay, so we are ready to do the sums and differences of sinusoids. Sums and differences of sinusoid. So let's go ahead and bring out your calculators. And I would like you to go ahead and graph this. Okay, go ahead and graph this for me. Okay, is that sinusoidal?
Whoa.
Not sinusoidal, right? Because like, ooh, like kind of all over the place, right?
Oh, my hands switched now.
So it's not sinusoidal. Okay, is it periodic?
Yes.
It is periodic because it repeats itself, right?
Yeah.
It does repeat itself, right? Because think about it. If this was f of x, right? F of x plus 2 pi is going to be equal to wherever x is. I'm going to put wherever x is, I'm going to go ahead and put x plus 2 pi, right? Which becomes 5 sine 2x plus 4 pi for cosine 3x plus 6 pi, right? But cosine 2x plus 4 pi is the same as sine of 2x, right? Because it's 2 pi plus 2 pi, so you just went the same thing, right? So this is basically the same thing as that. Same token, this is 6 pi, so it's the same as that, which is basically back to this guy, which says f of x. So you have proved that f of x is periodic by 2 pi, right? It is periodic, not sinusoidal though, right? Okay, so we're here. What if I gave you, since you already have that, what if we did this? See if that makes any difference. Is that sinusoidal? No, no, it's not, right? What if I gave you the same amplitudes? Does that make a difference? I change this to plus now, and this is 5. Is it sinusoidal?
No.
No, it's not sinusoidal, right? What if I go to change this back to 4, we change this to 2?
Now we're
Is it sinusoidal?
yeah.
And periodic, right? It's obviously periodic, but it's actually sinusoidal now, right? Okay, so here's the thing that out of this, what we should have learned is that when the b terms, or since if the b terms are the same, the period is going to be the same, right? The period is going to be equal to 2 pi over b, correct? Right? So in other words, if the b terms are the same, it has the same period and becomes sinusoidal. Okay? So when you're looking at a sum or a difference of sine and cosine, you look to see if these guys are the same. If they are the same, it is sinusoidal. If you look at page 372, top, there's a blue box. Read that for me. Example number 6. Determine whether each of the following functions is a sinusoidal or not.
Let's see.
Which one is?
A and G.
A and
D.
D, right? Even though we haven't talked about the adding 3 different ones, okay? As long as the periods are the same, then it would be a sinusoidal, okay? Okay. Example number 7, expressing the sum of sinusoids as a sinusoid. Okay, so we're going to go ahead and now, example number 7, we are combining y 2 sine x plus 5 cosine x. Okay, from the okay, so A, find the period of f. Find the period. What's the period? The b terms are the same. They're both 1, right? So the period is going to be 2 pi divided by b. So it's 2 pi divided by 1, which is 2 pi, correct? B, estimate the amplitude of the phase shift graphically. So graph it up. Tell me what the amplitude is by tracing it.
And what is the distance from the, no, I'm thinking of wavelength, sorry.
So estimate the amplitude and the phase shift.
It's 5.
5? How can it be 5? This alone is 5. Look at your graph. Look at your graph. Graph it and find out. I'm not asking you to do this algebraically. Also find the phase shift.
.37.
5.37. The book says 3.9. 3.9?
How would you get that exactly? Is there like a button to see this?
You can actually set how fast the trace goes, right?
Please tell me how.
You're going too far. Your increments are too big, maybe.
Like the window's too big?
No. The increments that you trace.
How do you change the trace?
Figure that out. I don't know. But 5.39 is the correct answer, right? Now, if you consider this to be a sine graph, right? If this was a sine graph originally, and you shifted it horizontally, so you have to find, I want to get you to find this point right here to tell me how much you shifted it. So negative 1.19. So I shifted it to the left 1.19. Can you see that? Right? Because normally if it was a sine graph, this point would be at the origin, right? But I shifted it to the left. So if I'm going to write this in the form where y is equal to a sine x minus cb plus d here, right? Which is a normal sinusoid. This is what a sinusoid looked like. Okay, so our A is the amplitude. We have found the amplitude to be 5.39, right? And we know it's a sine. We know that the B is 1 because it is 1, right? The periods were 2 pi, right? So we know that B is 1. But now I made a shift, but I shifted to the left. So when I shift to the left, I actually add 1.19. And y-wise, I didn't do anything y, right? I didn't shift it up or down. So there is no D. So this is what it's going to look like. Okay. Just as a FYI, since this is 2, and this is 5, if I had a triangle that looked like 5 and 2, what would this other one be?
Square root of 29.
Which is Go do your calculator.
Okay, thank you. 5.4.
5.39.
Ding, 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 ding. We have a winner.
Oh.
Whoa.
That's how you get it.
So this guy here is really this guy. Okay? All right? Okay? Keep that in the back of your mind. It'll come back. Example number 8 we already did, so I'm not going to do it again. This was the first time when we said, yes, it is not a sinusoid, but it is periodic. And this is how we proved that, right? We did that. So let's move on to damped oscillation. Damped oscillation is something that is actually happens every day in your life. You're not aware of it.
Sound waves. Oh, you are now aware of your breathing.
Damped oscillation. Damped oscillation is where something oscillates between graphs. So in other words, remember we had y is equal to x squared sine x, right? We did this and it was between this, right? Anybody want to hazard a guess what this parabola is? It's probably x squared, right?
Yeah.
This one's going to be y is equal to minus x squared. So it's oscillating between those 2 points. Okay. If I went by a tree, grabbed one of the limbs, and I let go, what's going to happen to it? It's going to go back and forth, and come back to its original position, right? So isn't that kind of a form of damped oscillation? Right? What about if I threw a pebble in a lake, right? Same thing, right? It kind of goes like this and then goes down, 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 down. And just as the energy dissipates, it goes back to like this, right? It's the same thing. There's so many things in nature operate as a damped oscillation. Okay. If you go to page 373 on the bottom, there's definition. Graph of y is equal to f of x cosine bx or f of x sine bx oscillates between the graphs of y is equal to f of x and then minus f of x. And we did this, right? F of x, f of minus f of x, right? Okay. And oscillates between those, and it's called damped oscillation or a damping factor. So let's go to example number 9. Graph those 3 and tell me which ones are damped oscillation or, wait a minute. So for each of the following functions, determine if the graph shows damped oscillation. If it does, identify the damping factor and tell where the damping occurs. Okay?
I think it's probably the first.
So graph it. Graph all those ABCs and tell me which one has a damping factor. Which one damps it?
Yeah, what if it just goes
If it
into a
goes
line?
down but then doesn't go back out.
That's damping. Yeah, that is
Oh,
damping.
okay.
So A would be damping, right? Because what is the factor?
Whoa,
Big number.
isn't it just 2 to the?
Oh, is it just
And
big
then-
numbers?
Goes like this, right?
Yes.
Right.
Pretty much.
So this guy here is going to be what? Y is equal to,
The power, yeah.
what is this actually? Isn't this the same as,
1
right? And it's a decay because this guy is less than 1, right? Remember we talked about decay versus growth when we talked about exponential functions? Something like that. Right? So it's in between the plus and the minus of those. So damping factor would be this guy, right here. This is the damping factor right here. Okay. So B, is B a damping oscillation, damped oscillation? Why not? Well, it just goes infinitely on and on and on, right? There is no change in the amplitude, right? So it's not, there's no damping there. What about C? Yeah, so in C we have what? Y is equal to 2x, y is equal to negative 2x, right? Y is equal to 2x, y is equal to negative 2x, and we're in between here, right? Like this, right? So the damping factor would be y is equal to 2x, y is equal to negative 2x. Example number 10. Dr. Sanchez's physics class collected data for an Airtable glider that oscillates between two springs. The class determined from the data that the equation that modeled the displacement of y, of the spring from its original position as a function of time t. Identify the damping factor. Well, what would the damping factor be there? Would be exactly e to the negative whatever, right? Everything before the cosine would be the damping factor, right? Okay. So basically what's happening is this. So I have a spring and I have a weight here, and I'm going to pull it or push it, and then I'm going to let go. So it's going to go up and down, up and down, up and down, up and down, and it's going to in the end, it's going to settle back to where it used to be, right? This is what's happening here. Okay, just kind of give you some context there. Okay. So identify the damping factor and tell whether the damping factor were good there. B, approximately how long does it take for the spring to be damped so that y is between -1 and 1? Well, you have to find out the first time it goes below -1 or 1, right? So if you go to page 375, can you see where they zoomed in there? Zoomed in there to find out when and where it becomes -1 or -0.1 or positive 0.1. So it looks like there first it's going to hit -1 first, -0.1 first, right? -0.1 first there. They zoomed in. They just traced it. Okay. So I'm never gonna ask you anything that's really, entailed here. Rather than I'm really more interested to see if you can identify whether it is damped oscillation or not. Okay, and if it is, what are the damping factors? So that's about as far as I'll probably go.
We don't have to do the tracing thing.
I could put that on the test, but really all that tells me is that you know how to go zoom in the window and trace it. Right?
Yeah.
What's the fun in that?
Yeah.
All right, we're done.